All right, lecture 52. A lot of terms there. We're going to use most of them in the next few lectures. All right, consider this reaction. Had to reduce the font size because it's just a large reaction. When 1 mole of barium hydroxide octahydrate reacts with 2 moles of ammonium nitrate, the reaction mixture absorbs 170.8 kilojoules of heat. Is the reaction endothermic or exothermic? What is the value of Q? Well, when it says absorbs, or heat goes into the system, that's endothermic. Case closed. So you have to learn to read, when it's given in words, you have to recognize what they're saying, which way is the heat going. If they say heat was emitted, that would be exothermic, heat leaves the system. Heat exits the system. You got to recognize what they're trying to tell you. And then what is the value of Q? Q is going to be plus 170.8. You don't have to put the plus sign. I would, though, just to state the difference. Exothermic, it would be negative. This had said that the reaction mixture gives up 170.8 kilojoules of heat. That would be a negative there. So recognize the difference between exothermic and endothermic, plus and minus, absorbs, emits, that kind of thing. Name 3 state functions and 2 non-state functions. Well, the ones that, enthalpy, H, is a state function, so we'll do state functions first here. U, internal energy, is state function. Volume, temperature, entropy, we don't really get into that at this stage. Next semester we do. But any of these functions where it only depends on the beginning and the end of the process, the initial and the final, where we don't really need to know the history of this system. These are some of them. So for instance, if you want to know something about, you have cold water and it's at, say, 10 degrees Celsius, and you leave the room and you come back and it's now a few hours later and it's at 21 degrees Celsius. You don't need to know how fast it took, how long it took to get there. Was it fast or slow? You don't need to know anything about what occurred during the time you were gone. You just need to know the initial temperature and the final temperature to know that the temperature change was 11 degrees Celsius. I'm trying to remember what I did. It's 10 to 21, so 11 degrees Celsius temperature change. But there are 2 functions that are not non-state functions, Q and W, heat and work. These ones you do need to know the history. It's not enough to know what you started with and what you ended with. You need to know what happened during that process. How are heat and enthalpy related? Now I'm going to go back to the book to make sure that it's in here. Sometimes I jump ahead. There's a thermochemistry chapter, thermodynamics chapter later, next semester. But yep, it's in here. So we have enthalpy, delta H, or change in enthalpy, and heat. But this is heat at constant pressure. When you see this subscript that is some term in thermodynamics, it means at that constant. So you can have Q at constant volume as well. You do Q at constant heat at constant temperature, and that wouldn't do much for you, but you could certainly do that. So anytime there's a subscript, that means at constant. Under those, that property is held constant. How are enthalpy and internal energy related? And we have H is equal to U plus PV. Enthalpy is equal to the internal energy plus PV. And in a real process, we only are interested in the change. So if we keep pressure constant, which is generally what we do in a lab setting, then the enthalpy is equal to the internal energy. So I'll put in enthalpy. The change in enthalpy is equal to the change in internal energy, and then this is the change in volume, and then the pressure, which is kept constant. So that is the relationship between them. When are they equal? Now, the reason we're doing this is that chemists tend to want to use enthalpy in their studies. It's still energy. It's still joules for enthalpy. But internal energy is what's used in thermodynamics. So the physicists use it. Why isn't it good enough for the chemists? Well, the reason is this term here. This is what we call PV work. It's the work due to a volume change when we have gases in our reaction vessels, which happens a lot. So if we studied the internal energy, we'd have this. And what that would mean is that we have to figure out how much heat is given off, because remember, delta H is heat at constant pressure, so the heat that's given off in the system. Plus we'd have to keep track of the volume change of gases, which means every single reaction would have to be done inside of a closed container that had a plunger system. It would be, as much as a lot of students don't like chemistry lab, imagine doing every single one of your experiments inside of a plunger system. It would be pretty horrible. So we switch it around, and then we only study the heat given off, and we know that incorporates the internal energy and the pressure or the volume change of the gases. So when are they equal? The only time that these two guys are going to be equal, the internal energy and the enthalpy and the internal energy, is when this term is 0. Well, the pressure is constant, and we assume that it's not 0. We're not working in a vacuum, so it's only when delta V equals 0. There's two times that this can happen. When there are no gases in the reaction, or when there are the same number of gases on both sides of the equation. Or the reaction. So this is important because internal energy and enthalpy are sometimes the same, but most times they're different in the same system. But if there are no gases present, then there's going to be no change in volume, so they're equal to each other. Or when the same number of gases are on both sides, since all gases, by the ideal gas law, have the same volume, then if we have 3 moles of gas on one side and 3 moles of gas on the other, even if they're different gases, the volume doesn't change, and so delta H is equal to delta U.